In mathematics, the Pythagorean theorem, also known as Pythagoras' theorem, is a relation in Euclidean geometry among the three sides of a right triangle. It states that the square of the hypotenuse is equal to the sum of the squares of the other two sides. The theorem can be written as an equation relating the lengths of the sides A, B and C, often called the Pythagorean equation, where C represents the length of the hypotenuse and A and B the lengths of the triangle's other two sides. Although it is often argued that knowledge of the theorem predates him, the theorem is named after the ancient Greek mathematician Pythagoras, as it is he who, by tradition, is credited with its first recorded proof. There is some evidence that Babylonian mathematicians understood the formula, although little of it indicates an application within a mathematical framework. Mesopotamian, Indian and Chinese mathematicians all discovered the theorem independently and, in some cases, provided proofs for special cases. The theorem has been given numerous proofs, possibly the most for any mathematical theorem. They are very diverse, including both geometric proofs and algebraic proofs, with some dating back thousands of years. The theorem can be generalized in various ways, including higher dimensional spaces, to spaces that are not Euclidean, to objects that are not right triangles, and indeed, to objects that are not triangles at all, but n-dimensional solids. The Pythagorean theorem has attracted interest outside mathematics as a symbol of mathematical abstruseness, mystique, or intellectual power. Popular references in literature, plays, musicals, songs, stamps and cartoons abound. Pythagorean proof. The Pythagorean theorem was known long before Pythagoras, but he may well have been the first to prove it. In any event, the proof attributed to him is very simple, and is called a proof by rearrangement. The two large squares shown in the figure each contain four identical triangles, and the only difference between the two large squares is that the triangles are arranged differently. Therefore, the white space within each of the two large squares must have equal area. Equating the area of the white space yields the Pythagorean theorem, QED. That Pythagoras originated this very simple proof is sometimes inferred from the writings of the later Greek philosopher and mathematician Proclus. Several other proofs of this theorem are described below, but this is known as the Pythagorean one. Other forms of the theorem. As pointed out in the introduction, if C denotes the length of the hypotenuse and A and B denote the lengths of the other two sides, the Pythagorean theorem can be expressed as the Pythagorean equation. If the length of both A and B are known, then C can be calculated as if the length of the hypotenuse C and of one side are known. Then the length of the other side can be calculated as, or the Pythagorean equation relates the sides of a right triangle in a simple way, so that if the lengths of any two sides are known, the length of the third side can be found. Another corollary of the theorem is that in any right triangle, the hypotenuse is greater than any one of the other sides, but less than their sum. A generalization of this theorem is the law of cosines, which allows the computation of the length of any side of any triangle, given the lengths of the other two sides and the angle between them. If the angle between the other sides is a right angle, the law of cosines reduces to the Pythagorean equation. Other proofs of the theorem. This theorem may have more known proofs than any other. The book The Pythagorean Proposition contains 370 proofs. Proof using similar triangles. This proof is based on the proportionality of the sides of two similar triangles, that is, upon the fact that the ratio of any two corresponding sides of similar triangles is the same regardless of the size of the triangles. Let ABC represent a right triangle, with the right angle located at C, as shown on the figure. Draw the altitude from point C, and call H its intersection with the side AB. Point H divides the length of the hypotenuse C into parts D and E. The new triangle ACH is similar to triangle ABC, because they both have a right angle, and they share the angle at A. meaning that the third angle will be the same in both triangles as well, marked as theta in the figure. By a similar reasoning, the triangle CBH is also similar to ABC. The proof of similarity of the triangles requires the triangle postulate. The sum of the angles in a triangle is two right angles, and is equivalent to the parallel postulate. Similarity of the triangles leads to the equality of ratios of corresponding sides. The first result equates the cosines of the angles theta, whereas the second result equates their sines. These ratios can be written as summing these two equalities results in which, after simplification, expresses the Pythagorean theorem. The role of this proof in history is the subject of much speculation. The underlying question is why Euclid did not use this proof, but invented another. One conjecture is that the proof by similar triangles involved a theory of proportions, a topic not discussed until later in the Elements, and that the theory of proportions needed further development at that time. Euclid's proof in outline. Here is how the proof in Euclid's Elements proceeds. The large square is divided into a left and right rectangle. A triangle is constructed that has half the area of the left rectangle. Then another triangle is constructed that has half the area of the square on the leftmost side. These two triangles are shown to be congruent, proving this square has the same area as the left rectangle. This argument is followed by a similar version for the right rectangle and the remaining square. Putting the two rectangles together to reform the square on the hypotenuse, its area is the same as the sum of the area of the other two squares. The details follow. Let A, B, C be the vertices of a right triangle, with a right angle at A. Drop a perpendicular from A to the side opposite the hypotenuse in the square on the hypotenuse. That line divides the square on the hypotenuse into two rectangles, each having the same area as one of the two squares on the legs. For the formal proof, we require four elementary lemmata. If two triangles have two sides of the one equal to two sides of the other, each to each, and the angles included by those sides equal, then the triangles are congruent. The area of a triangle is half the area of any parallelogram on the same base and having the same altitude. The area of a rectangle is equal to the product of two adjacent sides. The area of a square is equal to the product of two of its sides. Next, each top square is related to a triangle congruent with another triangle related in turn to one of two rectangles making up the lower square. The proof is as follows. Let ACB be a right-angled triangle with right-angle CAB. On each of the sides BC, AB, and CA, squares are drawn, CBDE, BAGF, and ACIH, in that order. The construction of squares requires the immediately preceding theorems in Euclid, and depends upon the parallel postulate. From A, draw a line parallel to BD and CE. It will perpendicularly intersect BC and at K and L, respectively. Join CF and AD, to form the triangles BCF and BDA. Angles CAB and BAG are both right angles, therefore C, A, and G are collinear. Similarly for B, A, and H, angles CBD and FBA are both right angles, therefore angle AB equals angle FBC, since both are the sum of a right angle and angle ABC. Since AB is equal to FB and BD is equal to BC, triangle AB must be congruent to triangle FBC. Since AKL is a straight line, parallel to BD, then rectangle BDLK has twice the area of triangle AB because they share the base BD and have the same altitude BK, i.e., a line normal to their common base, connecting the parallel lines BD and L. Since C is collinear with A and G, square BAGF must be twice in area to triangle FBC. Therefore, rectangle BDLK must have the same area as square BAGF equals AB2. Similarly, it can be shown that rectangle CKLE must have the same area as square ACIH equals AC2. Adding these two results, AB2 plus AC2 equals BD times BK plus KL times KC. Since BD equals KL, BD times BK plus KL times KC equals BD times BC. Therefore, AB2 plus AC2 equals BC2, since CBD is a square. This proof, which appears in Euclid's Elements as that of Proposition 47 in Book 1, demonstrates that the area of the square on the hypotenuse is the sum of the areas of the other two squares. This is quite distinct from the proof by similarity of triangles, which is conjectured to be the proof that Pythagoras used. Proofs by dissection and rearrangement. We have already discussed the Pythagorean proof, which was a proof by rearrangement. The same idea is conveyed by the leftmost animation below, which consists of a large square, side A plus B, containing four identical right triangles. The triangles are shown in two arrangements, the first of which leaves two squares A2 and B2 uncovered, the second of which leaves square C2 uncovered. The area encompassed by the outer square never changes, and the area of the four triangles is the same at the beginning and the end. So the black square areas must be equal, therefore A2 plus B2 equals C2. A second proof by rearrangement is given by the middle animation. A large square is formed with area C2, from four identical right triangles with sides A, B and C, fitted around a small central square. Then two rectangles are formed with sides A and B by moving the triangles. Combining the smaller square with these rectangles produces two squares of areas A2 and B2, which must have the same area as the initial large square. The third, rightmost image also gives a proof. The upper two squares are divided as shown by the blue and green shading, into pieces that when rearranged can be made to fit in the lower square on the hypotenuse, or conversely, the large square can be divided as shown, into pieces that fill the other two. This way of cutting one figure into pieces and rearranging them to get another figure is called dissection. This shows the area of the large square equals that of the two smaller ones. Einstein's proof by dissection without rearrangement. Albert Einstein gave a proof by dissection in which the pieces need not get moved. Instead of using a square on the hypotenuse and two squares on the legs, one can use any other shape that includes the hypotenuse, and two similar shapes that each include one of two legs instead of the hypotenuse. In Einstein's proof, the shape that includes the hypotenuse is the right triangle itself. The dissection consists of dropping a perpendicular from the vertex of the right angle of the triangle to the hypotenuse, thus splitting the whole triangle into two parts. Those two parts have the same shape as the original right triangle, and have the legs of the original triangle as their hypotenuses, and the sum of their areas is that of the original triangle. Because the ratio of the area of a right triangle to the square of its hypotenuse is the same for similar triangles, the relationship between the areas of the three triangles holds for the squares of the sides of the large triangle as well. Algebraic proofs. The theorem can be proved algebraically using four copies of a right triangle with sides A, B and C, arranged inside a square with side C as in the top half of the diagram. The triangles are similar with area, while the small square has side B minus A and area 2. The area of the large square is therefore, but this is a square with side C and area C2. So a similar proof uses four copies of the same triangle arranged symmetrically around a square with side C, as shown in the lower part of the diagram. This results in a larger square, with side A plus B and area 2. The four triangles in the square side C must have the same area as the larger square, giving a related proof was published by future U.S. President James A. Garfield. Instead of a square it uses a trapezoid, which can be constructed from the square in the second of the above proofs by bisecting along a diagonal of the inner square. To give the trapezoid as shown in the diagram, the area of the trapezoid can be calculated to be half the area of the square, that is, the inner square is similarly halved, and there are only two triangles, so the proof proceeds as above except for a factor of which is removed by multiplying by 2 to give the result. Proof using differentials. One can arrive at the Pythagorean theorem by studying how changes in a side produce a change in the hypotenuse and employing calculus. The triangle ABC is a right triangle, as shown in the upper part of the diagram, with BC the hypotenuse. At the same time, the triangle lengths are measured as shown, with the hypotenuse of length y, the side AC of length x and the side AB of length a, as seen in the lower diagram part. If x is increased by a small amount dx by extending the side AC slightly to d, then y also increases by dy. These form two sides of a triangle, CDE, which is a right triangle approximately similar to ABC. Therefore, the ratios of their sides must be the same, that is, this can be rewritten as follows. This is a differential equation which is solved to given the constant can be deduced from x equals 0, y equals a. To give the equation, this is more of an intuitive proof than a formal one. It can be made more rigorous if proper limits are used in place of dx and dy. Converse. The converse of the theorem is also true. For any three positive numbers a, b, and c such that a2 plus b2 equals c2, there exists a triangle with sides a, b and c, and every such triangle has a right angle between the sides of lengths a and b. An alternative statement is, for any triangle with sides a, b, c, if a2 plus b2 equals c2, then the angle between a and b measures 90 degrees. This converse also appears in Euclid's Elements. If in a triangle the square on one of the sides equals the sum of the squares on the remaining two sides of the triangle, then the angle contained by the remaining two sides of the triangle is right. It can be proven using the law of cosines or as follows. Let ABC be a triangle with side lengths a, b, and c, with a2 plus b2 equals c2. Construct a second triangle with sides of length a and b containing a right angle. By the Pythagorean theorem, it follows that the hypotenuse of this triangle has length c equals square root a2 plus b2, the same as the hypotenuse of the first triangle. Since both triangles' sides are the same lengths a, b and c, the triangles are congruent and must have the same angles. Therefore, the angle between the side of lengths a and b in the original triangle is a right angle. The above proof of the converse makes use of the Pythagorean theorem itself. The converse can also be proven without assuming the Pythagorean theorem. A corollary of the Pythagorean theorem's converse is a simple means of determining whether a triangle is right, obtuse, or acute, as follows. Let C be chosen to be the longest of the three sides and a plus b greater than c. The following statements apply. If a2 plus b2 equals c2, then the triangle is right. If a2 plus b2 greater than c2, then the triangle is acute. If a2 plus b2 less than c2, then the triangle is obtuse. Edgar Dijkstra has stated this proposition about acute, right, and obtuse triangles in this language. SGN equals SGN, where alpha is the angle opposite to side A, beta is the angle opposite to side B, gamma is the angle opposite to side C, and SGN is the sine function.